Okay, thank you. First of all, I want to thank the organizers for the opportunity to give a talk at this conference. And I will start with a short outline of my talk. I will state the problem that I am considering. I will consider Hilbert space. I will state the Cauchy problem for the Schrödinger equation and introduce some additional notation. Then I will formulate my main result, and then I will consider. I will obtain by the means of my main result the exact non-Markovian evolution of certain model, and I will consider some widely known in physical literature approximate master equations in the called Born approximation, and show that these approximate Born master equations predict these called coherences exactly. And I also consider the problem which was addressed by Bogolyubov and was discussed by Igor Vasilievich Volovich this morning about obtaining irreversible quantum evolution from reversible Schrödinger equation. Here we will see some widely known equations from irreversible quantum dynamics. And I will conclude my talk. Well, I consider the following Hilbert space. It is C to the power n+1 with poitent one-dimensional complex subspace, and it is in tensor product with n Bose-Fock spaces. In this, here's the numbers for, here's my notation for the basis in this n+1 dimensional space. The pointed subspace related to the zero basis vector, and here's one could define in this Fock space the pairs of creation and annihilation operators, and the vacuum vector or cyclic vector. Well, I consider the following Schrödinger equation. It is an n-level system of the following type. Actually, it is n+1 by n+1 matrix, but in this pointed subspace, it is just zero. I consider the similar reservoir, namely they are X in different Fock spaces, but they have the same dispersion functions. Then I will introduce the interaction Hamiltonian in the rotation wave approximation. It's stated here. One could see the so-called number of excitations is conserved here. This is most important for this Hamiltonian and for the results of my talk. Then I state the initial condition at with reservoirs at zero temperatures. It stays here, and I want that functions jk and omega k would be such that this integral converge and define the continuous function. It is nothing else but the reservoir correlation function. And I also define the reduced density matrix of the system of my n+1 dimensional system by the following formula. I am tracing out these Fock spaces. Well, the main result is here. If the vector psi is the solution of the Cauchy problem defined above, and condition 1 is satisfied. This condition is nothing else but that the correlation function is well defined. Then the reduced density matrix defined on the previous slide could be calculated by the following formula. And where this wave vector is uniquely defined as a solution of integral differential equation, which is stated here. Everything, this operator was in the definition of the Hamiltonian, and G is the correlation function. Well, one could use this result, for example, to test the approximate master equation. Here's the one which is widely known in the physical literature. Then, as I know, there are no strict mathematical derivation of it, so it is interesting to analyze in which cases it is true or not. So it is usually has to be written in the so-called interaction picture, but if we want to approximate the matrix of the system, which was in the previous part of my talk, they are interrelated by this formula. So then the most clear result here, the following, that this approximate equation predicts these non-diagonal elements of the matrix, of the density matrix of the system exactly, without any approximations. But it is only for coherences between this zero-pointed subspace and other subspaces. From the physical point of view, it is coherences between a ground state and the excited states. They could be measured by the means of spectroscopy, so it is they are physically it is interesting to obtain from the physical point of view. At the same time, it is possible that for other elements of these reduced density matrices, that they could be definitely not the same. Moreover, the diagonal elements of this matrix could be less than zero, so there are no good probability meaning, which we usually have in quantum mechanics. So this approximation good for coherences of this type, but for other elements of the density matrices, it could be very bad and since it's unphysical.
Извините, а это что, дефект вашего приближенного выражения для матрицы плотности?
Well, I have exact solutions, but I consider this equation that is widely used in physical literature. So it is defect of this widely used in physical literature equation. I'm just trying to show, but interesting that they usually calculated just these elements that interested from the point of view of spectroscopy and obtain good results. But it is just because they see only these coherences. So it's interesting from this point of view.
Это не ваша ошибка, это ошибка других.
Да, и получается, что люди ошибают, то есть то, что в тех вещах, которые они считают, они случайно оказываются правы. И это интересно. Now I will consider the very special case of the spectral density, or very special case of the correlation function, this exponential correlation function, and so this Lorentz type spectral density. Also, one could consider several Lorentz peaks. It could be found in this my archive preprint. So then one could obtain the following results, that this wave vector in the to n dimensional Hilbert space satisfy the Schrödinger equation with non-Hermitian Hamiltonian. It is also interesting because in some physical literature they introduced this Hamiltonian by hands, but it is interesting to derive it, and here we done it in some sense. And then, but usually in mathematical physics we use Markovian master equations. For quantum case, it is the so-called Garini-Kosakovsky-Sudarshan-Lindblad equation. It has the following form, and it is interesting to, one could easily construct by reconstructing the normalization by the following formula, the density matrix which satisfy actually this Garini-Kosakovsky-Sudarshan-Lindblad equation. So we start with reversible evolution, but we derive this also widely used evolution which is irreversible. But there are some tricky things because we have very special definition of this density matrix, but it is possible to prove it is well defined, and it also defines the evolution of the system. It is something like evolution of the system and some copy of the system. Usually it's called pseudo-modes in physical literature. But here we have exactly derived some irreversible evolution from initially reversible.
Означает ли, что это рост тильда удовлетворяет двум разным уравнениям?
Ну, у меня пси с волной от t удовлетворяет там, какому-то уравнению, и дальше я строю по нему рост тильдой. Это слегка, то есть смысл в том, что...
Тильда Косаковский-Линдблад, а физ
да.
Это вот то, что вы писали раньше с буквой Ж.
Да. Но интересно, что если мы правильным образом, скажем так, вырежем часть из этой ростильды, то мы получим точную динамику матрицы плотности системы, и в точности такую, как если бы мы взяли исходную унитарную динамику и взяли след по резервуару. Ну, вот для такого специального резервуара со специальной матрицей, спектральной плотностью. Well, the bottom line is that the finite dimensional integral differential equation was obtained, which defined the evolution of the reduced density matrix. These results are applied to the study of approximate non-Markovian master equations, and in the Lorentz spectral density case, we have connected the initial reversible evolution with several approaches to the irreversible evolution, like non-Hermitian Schrödinger equation and Garini-Kosakovsky-Sudarshan-Lindblad equation. So that is all.
У меня вопрос на понимание. Означает ли, что вы тем самым вывели заново Косаковского, Линдблада и прочих остальных уравнения из обратимой динамики?
Ну, здесь ситуация в том, что я выбрал в очень специальном, то есть у меня при нулевой температуре резервуар, то есть у меня очень специальное уравнение Garini-Kosakovского-Sudarshan-Lindblада я из очень специального резервуара вывел, но это не произвольное уравнение Garini-Kosakovского-Sudarshan-Lindblада. То есть вот такое расширение до унитарной динамики произвольного уравнения Garini-Kosakovского-Sudarshan-Lindblада мне неизвестно.
Но все равно, это ведь Garini-Kosakovский-Lindblад выводится обычно с каким-нибудь там в пределе лямбда к квадрату.
Да, а вот здесь мы ничего такого не сделали. Да.
То есть это альтернатива по существу?
Ну, в некотором смысле да. В некотором смысле да. Спасибо.